In this session we do the other part of the two-part IFF if and only if type proof. We finished the if part, and now we do the only if part. Now typically, as saying a bit earlier, an if and only if type proof will involve two mathematical statements, P and Q, and the theorem statement will be something like P IFF Q. In other words, P is true if and only if Q is true. Now we're doing the only if. We're doing the proof of the only if part. Remember, an if and only if type theorem requires two proofs, both directions. If P then Q, if Q then P. And we're doing now the only if part. So it would be P only if Q. So in other words, the only way you can get P is if you had Q. So if you do have P, you must have had Q. So in other words, if P then Q. Okay? In other words, you start with the statement, in other words P, on the left, your left-hand side, and arrow to Q. So if P then Q, that's what we're trying to prove. Okay? Here, P to Q. P only if Q. So P arrow Q. Now what is P? Well, here's the only if part. Sipser puts as a lemma. Remember, lemma is just like a preliminary smaller proof that gets used as a part in a larger proof coming later. So lemma 1.60. So here's the actual statement. So if a language is regular, okay, then it's described by a regular expression. So let this statement here, the language is regular, call that P, then, and here's your statement Q. It, that just means a language, is described by a regular expression. Call that Q. Right? So we have, and it's the only if, so we have to prove if P then Q. In other words, you start with P, you start with that's your left-hand side, and you have to prove this. So you're starting with the language is regular. That's your P statement. Alright? So, as usual, with Sipser, it's a good idea. He starts with an outline, an overview of the proof. So proof idea. And, well, we don't we have two more sessions and we still don't get onto the actual proof, the detailed proof. Because to get to that stage, we need more knowledge. We need new concepts. And in this session, I mentioned a bit earlier, a couple of sessions back, that we'll introduce a new kind of NFA. Call it a generalized NFA. So we need to talk about that and how it works and so on. And that'll take quite a while before we get to the actual proof, pulling the two lemmas together, the if part and the only if part, and then finally finish the theorem, the proof of theorem 1.54, which is proving the equivalence between an automaton that recognizes a language and a regular expression that describes that language. It's the same language, then the machine, the automaton, and the regular expression, they should be equivalent. Your intuition says that if you're talking about the same language, as I've said before. Right, okay, so this is our P and this is our Q, so we start with this P, we start with the idea a language is regular. And what does that mean? For a language to be regular, what's the definition of a regular language? Well, it means it's a language that's recognized by some automaton, okay? Some DFA. That's the definition. So in other words, to prove if P then Q, we have to show that the machine that makes this language regular, yeah, the machine that recognizes that language, some DFA. So effectively, this proof here, this lemma, it boils down to showing that there is a DFA that so from that DFA you can get a regular expression that describes the language. Now, what I've just said is critical. It's like the heart of the proof. Play it back. Rewind if you need to do it again. Yeah. So if the language is regular, therefore there is a DFA that recognizes it. Okay. And from that DFA, we will create a regular expression. That's the heart of the proof. Now, concentrate, because the logic gets more complicated. All right. So what things have boiled down to now is we from the DFA we now create a regular expression that describes the language. Which language? Well, the language the DFA recognizes. Right? Now, to do that, to go from a DFA into a regular expression, we need two steps. Okay? And the first step is to translate the DFA into something called a GNFA. Now, the N is still just non-deterministic, okay? So I'll explain what this is. But so that's the first step. So I'll say it again because it's important. We start with the DFA, the deterministic finite automaton. This DFA, and the DFA is the machine, the automaton, that recognizes the language. Okay. And from that we have to get a regular expression. So we're trying to go from DFA to a regular expression. And we do that in two steps. So think of this middle step. Like DFA, that's like your starting step. And then the regular expression, that's your final step. But we do it in two stages, two steps. So this is like this middle step. And that is the generalized GNFA. Okay? So in other words, you will convert your DFA into this middle step a GNFA. NFA. It'll be a non-deterministic machine. So you'll go from DFA to GNFA, and then from that it's much easier to convert the GNFA into a regular expression. Okay, so I'll sort of summarize it a bit. From DFA into GNFA into a regular expression. Okay, so with that two-step process, it's sort of it's equivalent to going in one step direct. From a DFA to a regular expression. But that's hard, so we split it up using this new concept of a GNFA. Right? And I haven't explained to you what that is, that'll take quite a while, several sessions. But doing that two-step process makes things easier and doable. Okay, so let me sort of bring it all together in a sense. To prove this lemma, the language is regular. If a language is regular, it has a DFA, right, that recognizes that language. Okay, so there's a DFA. We're told this language is regular. That's P. Right? The language is regular. Therefore, it has a DFA that recognizes it. Okay, so we have the DFA. From that DFA, we convert it to a GNFA, right? It's the middle step. And then from that, it's much easier to convert the GNFA into a regular expression. Okay? So we had those three parts here, but we were, like at the beginning,